So this was nothing more than seeing if you understood that the one fact is the probability of S happening is 1. Something has to happen, and the sum of all the probabilities is equal to 1, and that enables us to find X. By the way, I should remark that some of these problems can be solved a couple of different ways. Now let's look at problem number 2. In problem number 2, I gave you P of A prime was 3/5. And what else did I give you? I gave you.
You gave us P of A equals 2/5.
Oh, okay. So let me see what I gave you. So I gave you P of A was 2/5.
P of B was 1/5.
P of B is 1/5.
And then you had P with that line of A complement equals 1/10.
P of B given A complement is 1/10. Okay. Now there are a couple ways of doing this problem. The easiest way is using a Venn diagram. Some people use some formulas. Okay. So if we just look at this term right here, by the way, firstly, we now know, of course, that P of A complement, in case we need that, is 3/5. And P of B complement will be 4/5, right? Now, if we look at this term here, this says P of B intersection A complement over P of A complement. This is 1/10. But P of A complement, we found above, is 3/5. So this tells me immediately, in case I need it, P of B intersection A complement is 3/50. If I cross multiply, right? 3/50. So while I could use formulas, and some of you did it that way, I think it's a lot easier just to draw a picture and see what's happening. So here, say, is A. Oops. Here's B. Okay, so what do we know? P of B intersection A complement, where is that? That's right here, right? And that's 3/50. Maybe I should switch to red here. Okay. So this is 3/50. Now I know B, P of B is equal to 1/5, which is 10/50. So that means this must be 7/50. And what was A? A was 20/50. So this is 13/50. So what did I ask you to find here? I asked you to find P of A intersection B. Well, that's just 7/50. And what else did I ask you to find? I don't remember. P of A given B complement, was that the one I wanted? And if you wanted to, you just say this is just P of A intersection B complement over P of B complement. P of A intersection B complement is 13/50 divided by P of B complement, which is 40/50, which is 13/40. You could have done this using formulas, and some of you did it that way. You didn't need a Venn diagram. That would have been fine. I want to remark, a couple of people did the following. P of A intersection B is not equal to P of A times P of B. In fact, we know that P of A given B is equal to P of A intersection B divided by P of B. So in fact, P of A intersection B is equal to P of A given B times P of B. So notice this is not P of A. We'll see under what conditions it will be. In fact, if you think of it in terms of a tree, if this is A and this is B, here's P of A, here's P of B given A, and right here is P of A and B would be the product of these two. So one way of writing it is this way. If I started with the B and then I did the A, it's also equal to P of A given B times P of B. It's not equal to the individual product. We'll see the only time that's going to be true is when they're independent, whatever that might mean. Okay, so then I asked you true or false. And I asked you for a reason, and some of you gave me lousy reasons. And what was it that I wanted to ask you to prove? Is P of B intersection A complement, is that equal to P of B minus P of A and B? Now, what some of you did, and I accepted it in most cases, you gave me a picture by means of a Venn diagram, and I accepted that, and that's a reasonable kind of proof, but it was a little sketchy. Actually, the way to observe it is as follows. Notice, if this is A and this is B, if you look at your Venn diagram, notice that A intersection B union with A complement intersection B is equal to B, right? This piece right here is A intersection B plus this piece in red together give me B. Now notice these two events are disjoint. How do I know this? They're disjoint. If I take their intersection, when I can do this in any order, A intersection A complement is the empty set, so this is going to turn out to be the empty set. Therefore, P of A intersection B plus P of A complement intersection B equals P of B. Bring this over to the other side and you've proven it. That's more of a formal proof. But if you did it by means of Venn diagram, saying that you can see that P of B is just equal to P of A intersection B plus P of A complement intersection B, and then just bring it over, that would have been an acceptable proof. Okay. By the way, if there are questions along the way, now is the time to ask them, okay? The next problem, I gave you 5 men. Where am I up to number 4A? There are 5 men and 6 women. I asked, what's the probability that if they stand in a line, they alternate? Notice I said probability. I didn't ask how many ways. Well, firstly, we have 11 people. Total number of ways they can stand in line is 11 factorial. Now, if A is the event that they alternate, notice 1, 2, 3, 4, 5, 6. I don't have enough room here. Let me do it in the next line. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Notice I have 6 women and 5 men, which means I don't have enough spaces for both of them to alternate. I have to start with a woman, because that'll take 6 spaces. 1, 2, 3, 4, 5, 6. So that would be 6, 5, 4, 3, 2, 1. And now the rest will be men, and there are 5 of them. 5, 4, 3, 2, 1. And this is just 6 factorial times 5 factorial. So the probability will just be 6 factorial times 5 factorial over 11 factorial. And by the way, this is pretty easy to calculate. If I go 11, you didn't have to, 10, 9, 8, 7, 5, 4, 3, 2, 1. And if you actually work this out, you get 1 over 462. But this was certainly an acceptable answer. Okay, that was A. What was B? I don't remember what the, let me, we had a total of 7 people, was that correct? And how many candy bars did we have? I had 12 candy bars. And I asked, what's the probability that the oldest gets how many? At least 4? Okay. Well, firstly, in how many ways can I distribute the 12 candy to the 7 people? Well, this is clearly stars and bars. If there are 7 people, then I'm going to have 6 bars and 12 stars. So the total number of ways that could happen, it can be distributed, is 18 choose 6 or 18 choose 12. That's going to be my denominator in finding the probability. And now I still have 6 bars. If I give 4 to the oldest, that means there are 8 bars left, 8 stars left rather. And I distribute those, and that will just turn out to be 14 choose 8 or 14 choose 6. So the required probability is 14 choose 8 divided by 18 choose 12. And I didn't require you to work it out, but if you did work it out, I believe the answer is 11 over 68. Okay. The next problem is we had 3 red, 2 green, 4 yellow, and 7 black, was it? And I draw 8. Well, the total number of ways I can draw 8 marbles from the, what do I have at 5, 9, 16 altogether is 16 choose 8. Now, if I want 1 red, from the 3 red, I choose 1. And I wanted 1 green. And I wanted 1 yellow. And the remainder are going to be black. So by the multiplication principle, there's the numerator. And then whatever this is, you can work it out. Okay. Fine. So then I asked the following. X cubed minus 1 over 2x, was that squared, to the 10th power. And I asked, what's the coefficient of x to the 5th? Now, some of you tried to use Pascal's triangle. Somehow you guessed. Somehow people guessed automatically that k, whatever that turned out to be, is 5 without doing any work. You only got that luckily. That's not the way to do the problem, and you just got lucky that you got k equal to 5. Your solution was not the correct solution. So we want to, when you expand this, let's suppose we call it a plus b to the 10th. Any term would have the form of, well, firstly, it'll be of the form 10 to the k, any term in this expansion. Then it will be 8 to the k, b to the 10 minus k. Where a in this problem is equal to x cubed, and b is equal to minus 1 over 2x squared. And now we have to find out what k is in order to compute the coefficient. Well, let's substitute. So we have 10, choose k, A is equal to x cubed. B is equal to minus 1 over 2x squared to the 10 minus k. And by the way, you could have switched these powers. You could call this one 10 minus k and this one k. It doesn't make a difference. So let's do this. This gives me 10 choose k. You have to determine the k. You can't just guess that it's 5 because 5 and 5 add up to 10. This is x to the 3k. This is minus 1/2 to the 10 minus k. I'm using the laws of exponents. And 1 over x squared to the 10 minus k. So this gives me 10 choose k minus 1/2 to the 10 minus k, x to the 3k divided by x to the 20 minus 2k. This power becomes x to the 5k minus 20. And what do I want this power to equal to? I want this power to be x to the 5th. So this has to be a 5. So I get 5k minus 20 must be 5, or solving k is 5. So coincidentally, some of you were able to guess that it was 5, but that's not a solution. Now, if k is 5, then the coefficient is 10 choose 5 minus 1/2. 10 minus 5 is 5. And this turns out to equal to minus, what did I get finally? 63 over 8. So in fact, the term in the expansion that I wanted, the answer was minus 63 over 8, x to the 5th. That would have been the actual term in the expansion if you expand it. Guessing it's equal to 5 is not a solution. And using Pascal's triangle is not a solution. Okay, the next problem. We have an urn or whatever. And what did I tell you? We had n black and 6 white. And we drew 2. What's the probability? And I tell you the probability that they're both black was equal to, what did I say that was?
2 out of 11.
2 out of 11. I want you to know how many black are in the urn. Well, there are a couple ways of doing this problem. One way is, well, the first one is either black or white. The probability it's black would be n out of n plus 6, right? If the first one is black, the probability the next one is black is n minus 1, right? Because there's 1 fewer black, over n plus 5. And here's the event right here that they're both black. So n minus 1 over n plus 5 times n over n plus 6 is equal to 2 over 11. By the way, I'll finish in a second. Alternately, I want to choose, I could have done the problem this way, right? Over n plus 6, choose 2. That's another way of doing the problem, right? I want 2 black from the n and the total number of ways are n plus 6 balls altogether, I'm choosing 2. This will give you the same, and this would equal to 2 over 11. So now I have n times n minus 1 over n plus 5 times n plus 6 is 2 over 11. If I cross multiply this, what did I get? If I cross multiply, I end up with, and then solve it, I get 9n squared minus 33n minus 60 equals 0. Well, if I divide by 3, I got 3n squared minus 11n minus 20 is 0. We all learned how to factor or use a quadratic formula, whichever one you want. And this gives you 3n plus 4 times, what do I get? N minus 5 equals 0. This gives me a negative solution. I reject it. This gives me n equal 5. Bingo, the problem solved. There are 5 black balls. This is a mathematical solution. I cross multiply. That's called, I solved this problem. It's called algebra 1, right? Clear fractions. That's what cross multiply is. Remember that A over B equals C over D. That means AD equal BC. I cleared fractions. Sometimes they say cross multiply. Okay. So that's called algebra. Next problem, we had 7 Republicans, right? So we had 6 Republicans and 1 female Republican. So these are the Republicans. And how many Democrats did we have? We had 5 Democrats, 4 Democrats, and 1 female Democrat, right? Yeah. And now I said we're going to choose a committee, and the committee is always going to have three Republicans and how many Democrats? 3 Republicans and 2 Democrats. Well, the number of ways that could be done is 7 choose 3 and 5 choose 2. So that's a total number of possible committees. Remember, I said every committee is going to have 3 and 2, not 12 choose 5. 12 choose 5 could be all it's possible that would happen. They'd be all Republicans or all Democrats. I wanted every committee to have 3 and 2. Okay. Now, in the first question, suppose I want both females to be so the denominator in each case is going to be 7 choose 3, 5 choose 2. Now, if I want both women to be on the committee, then I need from the Republicans, I need 2 more people from the remaining 6. And from the Democrats, I need 1 more person from the remaining 4. So that's the answer to A. Did I work that out? Yeah, that turned out to be 6 out of 35 if you work it out. Now, if you don't want them, it's not the complement, okay? If you don't want them, in part B, the denominator is still the same. So if you don't want either of them to be on the committee, then you still need 3 people from the remaining 6 for the Republicans, and you still need 2 people from the remaining 5 for the Democrats. And that turns out to be, by the way, 12 out of 35. Okay. Notice, this is not the complement. You got to figure out, make sure you understand why it's not the complement. Because there are other cases. It's possible you have one and not the other. Okay. A die is tossed 3 times. Determine the probability. What was the question? The sum is what? The sum is 5. Well, firstly, I know the denominator. If I toss a die 3 times, the total number of possible things that can show up is 6 times 6 times 6 or 6 cubed. So the question is, how many ways can the numerator get up to 5? Well, there are a couple ways of doing it. One way, of course, is to look at the possible cases. The first could be 1, the second could be a 1, that's 2, and then we get a 3. Or the first could be a 1. I want to get all my cases I worked in that. The second could be a 2, that's 3, and a 5. Or the first could be a 1, the second could be a 3, it's 4, and a 1 is a 5. I'll show you a better way of doing this in a minute. The first could be a 2, a 1, 2, a 2, 2, 1, and a 3, a 1, and a 1. And that's a total of 6 different ways. So the probability is 6 over 6 cubed, or 1 over 36. By the way, another way, without actually writing these out and getting these 6 cases, is to observe. I'm really asking if x1 is what I got, is this x2 and x3 is what I got in each toss. I want the sum to be 5, where x1 is greater than or equal to 1, x2 must be greater than or equal to 1, and x3 must be greater than or equal to 1. The total number of solutions of this is what we want to find, would be the numerator. So notice I have 5 stars. And I want each one, and there are 3 people, so there are 2 bars. But I want each one to be at least 1, so if I get each one, there are 2 stars left. And 2 bars left. And so this just gives me what? A 4 choose 2, which is 6. Same number I got here. Okay. That was number 8. Now number 9. Now we have, in number 9, we have 3 red and 7 blue in urn 1. And in urn 2, we had 4 red and 6 blue. And here's the rule. If you toss a die, and if you get a 1, 2, or a 4, you combine both urns, right? Well, if you combine both urns, then the probability of getting a red is 7 out of 20. And the probability of getting and the probability of getting a blue is 13 out of 20. And the probability of getting a 1, 2, or a 4 when you toss a die is 3 out of 6, or a half if you like. On the other hand, if you get a 3 or a 5, you choose a ball from urn 1. That's 3 out of 10. And this is 7 out of 10. And the probability of getting a 3 or a 5 is 2 out of 6, or 1/3. And lastly, if you get a 6, whose probability is 1/6, you just choose from the other urn red and blue, and that would be 4 out of 10, 6 out of 10. So the first question I ask was, what's the probability that you got a 6 and it was blue? Well, that means I got here on my tree. So that's 1/6. I'm sorry, which one am I doing now? You got a 6 and a blue. Okay, so it's 1/6 times 6/10 or 1/10. Okay, the next one was, what's the probability? I can't read my handwriting. It's a 6 or a blue.
is blue or a 6 is drawn.
Yeah, a 6 or a blue. Okay, well, this can be in a number of ways. One way is, the easiest way, I think, is the probability of getting a 6 is just 1 6. I'll do this a couple other ways for you. Now, how else can this happen? Well, so I've just shown one way it can happen is if I get right here, and I don't have to go any further. The other way it can happen is if I get here or here. Okay, so let me, so let's write that. So I get a 6 plus 13 over 20. Here's the other way it can happen. 13 over 20 plus times 3 6 plus 7 over 20, 7 over 10, I'm sorry. Times 2 6. And whatever that is, that's the answer. Alternately, you could have said P of 6 plus P of B minus P of B and 6. So P of getting a 6 is 1 6. This one I'll figure out in a second because that's the next answer. And minus P of B and 6 is 1/10. So how do I figure out the probability of blue? Well, that can happen 3 ways. It can happen 3 6 times 13 over 20.
Hey, Professor, do you also add the 6/10?
I'm sorry?
Do you also add the 6/10, like on the bottom?
From here, you mean?
Where the
From
red
here?
star is?
No,
Yeah, do you?
because you already took care of it by getting the 1 6. Once you got the 6, you've already won this game set. You've drawn it, you either a 6 or a blue. Well, you can get a blue this way and this way, and a 6 this way. I subtract off the thing when I'm doing this method here. There's a subtraction because when you compute the blue, you've also gotten the 6, so you have to subtract off. You can't count it twice.
Got it.
Okay, so now let me get the P of blue. So P of blue, remember, P of blue can happen 3 ways: this way, or this way. So that's 3 6 times 13 out of 20 plus 2 6 times 14 out of 20 plus 1 6 times 12 out of 20. I wrote it. I did everything over 20s, by the way. And this turns out to be just 79 over 120. Okay, so that was your exam. So now we'll talk about it. Some of you don't know what the hell you're doing, and that's pretty clear. Let me just go back down. You really have no idea, and either you got to ship up or shape out, basically. You haven't been doing your homework, obviously, because if you're doing your homework, most of these problems have been straightforward. Some of you don't know how to do simple algebra, which is kind of strange since you need at least 1 semester of calculus as a prerequisite for this course. So we're going to be using that pretty soon. So you need to figure out what happened here, why you didn't do well at all. Anybody got less than a 60 on this exam is really in a pretty dangerous situation, as I see it. The exam was not hard. It was straightforward homework exercises. You didn't have to do much arithmetic on the exam, and yet some of you have no idea what you're doing. So if you want to speak with me, we'll make an appointment, we'll talk, but there's a problem here, and it looks like you're not doing your work. You're asking very few questions, and when we meet about homeworks, which is indicative to me that many of you are not doing it. I offered you the opportunity of if you have questions over the weekend, write me. I think 3 of you actually wrote me, and I sent you solutions. If you don't do your work, you're not going to pass. I'm not Big Brother here. I'm not going to force you to do anything. But if There are not going to be no gifts here. You need to do your work. Okay, anybody have any general questions? I don't know. I didn't bother to figure it out. I figure out the average at the end of the semester. I think the highest, there were a couple of grades in the 80s. So, they were spattered around. But I'm more concerned about the grades below 60. Anything below 60, you're really in dangerous. I mean, if you got a grade in the 20s or 30s, you don't know what the hell's happening here. And you better correct that real fast or drop the course. Miracles are not going to happen. And this is the easier part of the course, what we're doing now. Permutations and combinations can be a little annoying, but the material gets more challenging as we continue. Okay, how are we doing time-wise? All right, I have time to. So now I want to talk about Bayes. I want to talk about the Bayesian problem, also called a posteriori probability. Posteriori, I don't know. Check the spelling, it's in the book. Okay. I showed you the last time that if we partition a set, meaning I break S up into n disjoint sets, that is, the intersection of these is the empty set if they're different. Then any event E can be written as E intersection A1 some of these could be empty, and the probability of E is n equal to the sum of the probabilities because they're all disjoint. These are unions, okay? And I can more succinctly write this using sigma notation as P of E is equal over all possible I values. So I goes from 1 to n. Sometimes I'll just write an I. And we observe that P of A intersection A sub I by the multiplication principle is equal to P of E given A sub I times P of A sub I. Or we get the law of total probability over all possible I values. And this was called the law of total probability. And in fact, one can actually see this by means of a tree. Suppose, for example, here's A1, A2, all the way down to A sub n. And there are lots of different ways of getting E1. I'm just drawing part of the tree. E1, I'm sorry, E, not E1. There are lots of different ways of getting, think of the problem there being n urns, and in each urn there are red balls. You draw, what's the probability of getting a red ball? So then the probability of E can happen in all these distinctive ways. It's just P of, remember this is P of E given A1. This is P of A1. This is P of E given A sub n. This is P of A sub n. So this just turns out to be the sum of P of E given A1 times P of A1. and so on. P of E given A sub n times P of A sub n, or just the sum I had above. P of E given A sub I times P of A sub I. So there's really nothing new here. This is just another way of looking at the tree, and we have the law of total probability. So what I want to do now is I want to show you how this could be used. And by the way, it's called the law of total probability. It's also called, some people call it conditioning. So let me describe when one uses a problem, when one uses this. Typically, a problem is to find what's the probability of A given B. Now, up until now, for the most part, we didn't really need a formula to do this problem. We just looked at the reduced sample space. And then from a reduced sample space, we were able to compute the problem. But now I want to answer this problem in a special case. In a special case when I'm giving you the outcome, sometimes called the effect, and I want to know, I'm asking about the cause. Okay? So in such a case, and this is an unusual problem, normally I tell you about the start of the experiment, I tell you about the cause, and I ask you what happens. What's the probability that this effect happens? Now I'm reversing the question. I'm giving you the effect, B now is the outcome, and I'm asking you about the cause. And let me give you an example similar to the one I gave you the other day. And to show you, this is the case, this is going to be called a Bayesian problem, but you need to recognize it. So again, here's the following. Suppose I have two urns. Say 10 red and 10 blue. This is urn one. And 5 red and 15 blue. And now let me describe the problem. An urn is chosen at random. But you don't know which urn was chosen. You saw the outcome, the ball drawn was red. Determine the probability. It came from urn one. So notice, here's the question. Given the ball was red, determine the probability it came from urn one. Now you notice that's a different question than the following. Suppose I ask, if it came from urn one, the probability that it's red. Well, if it came from urn one, the probability it's red is 10 out of 20, right? But that's not what I'm asking here. This is just 10 out of 20. What I'm asking here is I'm telling you the outcome of the experiment. I'm telling you the effect of the experiment. I'm asking you about the cause of the experiment. So when you recognize that this is the so-called, what I call, I'm giving you the effect and I'm asking you about the cause, you do this problem as follows. Use the definition of conditional probability. And now observe, this can happen a number of ways. This is the law of total probability. Notice if I put this problem on a tree, here's urn one, and here's urn two. The probability it's urn one is a half. I can choose these urns at random. If it's urn one, the probability it's red is 10 out of 20. was the other color? Blue. If it's earned 2, the probability it's red is 5 out of 20. So notice the probability that it comes from earn 1 and is red is just the event right here. This is I and R. By the multiplication principle, that's just 1/2 times 10 out of 20. The probability that it's red, notice it can be read 2 ways. It could be read this way, or it could be read this way, each part of the tree. And that's equal to 1/2 times 10 out of 20 plus 1/2 5 out of 20. So what does this give me? This gives me all denominators cancel, 10 out of 15, which is 2/3. Notice this term at the bottom is the sum of all the ways it can be read. That's the law of total probability. So in fact, very often you'll see a formula like this. P of, say, A sub I given E. Okay? That's the typical problem. I'm giving you the effect. I want to know about the cause. You'll often see, you don't need this formula. I'm just rewriting the formula now. So this is P of E given A sub I times P of A sub I. And this denominator is just all the ways it can happen. It's just the same formula. Let me give you another example. This is an interesting example to illustrate the importance of the Bayesian problem. How am I doing time-wise? Okay, I'm doing it. All right, fine. I'm taking this problem right out of the book. Suppose 5%, this is example 1 on page 83, I think it is. Suppose it's known that 5% of the population is infected with a virus. Okay. And moreover, 99% of the time, an infected person tests positive for the virus. Whereas a false positive occurs, what does it occur? 0.5%. We all know what false positives are now in these times, right? False positive, somebody who's not infected who tests positive. Determine the probability a person who tests positive has the virus. I will give you 3 or 4 minutes to set up this problem, okay? and then I'll work it out. Don't look at the book. See if you can set it up yourself. I'll be right back. Okay, how are we doing? Anybody having success setting it up without looking at the text? Notice, let me introduce some symbols. Can you guys hear me? I want to make sure, I just unmuted myself.
Yeah,
Somebody want to respond?
We can hear you, Professor.
Okay, great. So notice in this problem, the effect is the test, whether the test is positive or not. So if you look at any individual, they either have the virus or they don't have the virus. And the probability that they 5% have it, right? And 95% do not. Now, Now, 99% of the time, an infected person tests positive. So if you have the virus, you test positive 99% of the time, which means you test negative 1% of the time. I'm using percentages rather than decimals, okay? On the other hand, if you don't have the virus, we get what's called a false positive, and that happens, was that 0.5%? Was that 0.5? I lost a place. Let me see. Yeah, 0.5%. And therefore, this is 99.5%. And the question is, determine the probability of a person who tests positive. So given you test positive, what's the probability the person has the virus? There's the question. Now notice what's happening here. I'm being given the effect of this experiment here. The effect of the experiment is the test, whether the test is positive or not. And we're asking you about the cause. Do they have the virus or don't they have the virus? So we recognize this to be the so-called effect and cause. I'm giving you the effect and I want to know about the cause. I'm giving you the end of the tree and I want to know about the beginning of the tree, the start of the tree. That's the Bayesian problem. So that's one of the few times I use a conditional formula. Now, I want you to observe that I don't have to write out the formula for P of plus. There is a formula, like P of plus can happen two ways. You have the virus, you don't have the virus. That's the sum of all the possibilities. That's the law of total probability. But I can get it directly off the tree. So how can this happen? P of V and plus is the event up on top. That's 5% times 99%. And P of plus can happen two ways. One way is the upper part of the tree, or if the false positive way. Okay, now you whip out your calculator. Do I whip out my calculator somewhere? And this turns out to be 0.9124, or if you like, 91.24%. So look what this says. Now let's interpret the problem. Let's see if this test is any good. This means a little over 91% of the time, if somebody tests positive, they'll have the virus. Given the test positive, the probability you have the virus is a little over 91%. Now, is that a good number or not? The question is this a good test? Well, if you have 1 million people, or say 10 billion people, or maybe there's a pandemic and you have 300 million people, roughly a little over 90% of the time, let's look at the other way, almost 10% of the time, you're gonna get false positives. Now, 10% of say 300 million is a pretty big number, which means this is a pretty crappy test. I made up the numbers here. So you want, if this were a real life problem like a pandemic, and you wanted these nose tests that you take for COVID to be somewhat accurate, you'd like this probability to be like 99.9%. Otherwise, you're calling people back. 10% of the people are being called back with these false positives who have to be retested. So this kind of problem, this probability problem, this Bayesian problem is really an important problem, you know, for the so-called effect and cause. It gives you information about the cause of an experiment. So it has some real life important ramifications answering problems of this type. Okay, but it's easy to recognize. You recognize a Bayesian problem in a very simple way. Namely, you're being given the end of the tree, you're being given the cause, the effect of the experiment. And what you're being asked about is the cause of the experiment. So in that sense, it is an extremely important problem, and one needs to examine it in some detail. They're easy problems to do. Once you realize it's the Bayesian problem, then you just use a conditional formula, you draw the tree, or you don't have to draw a tree, you can use it with formulas if you like. For a basic problem, it's usually easier to draw a tree, but you don't have to. You can do it either way. Okay. Please make sure you do the homework exercises in section 2.4. So now I want to talk a little bit about independence. I'll talk briefly now. I can't do too much, but a little bit. Okay. So the question is, what do we mean when we say A and B are independent events? What does that mean? Well, if you think about it for a second or two, I'm sorry? No. It's possible to rig up problems where they're not. In fact, I'll give you I'll go through some examples in a minute. Okay. That is, we need to mutually exclusive means they can't happen together. But I can show you that, well, we'll see in a minute. We'll look at that difference because that's students mix up the two ideas of independence and mutually exclusive. Okay, but we'll see in a minute. A and B are independent if one outcome does not affect the other one. Agreed? If two events are independent, then one should have no effect on the other. So how can one define that? Right now, I'm just talking about two events. So if one has no effect on the other, then if B doesn't affect A, this should be true, correct? And similarly, and by the way, I can show that if one of these is true, so is the other one. If A is independent of B, then B is independent of A. So I could define A and B, the two events A and B are independent if P of A given B is equal to P of A. That's one way of defining it. And by the way, that's nice, but it doesn't generalize as easily as the next definition. On the other hand, we know that P of A given B is equal to P of A intersection B over P of B, correct? Now, if A and B are independent, according to my definition above, P of A given B is the same as P of A. B doesn't affect A. That means if I substitute, and then cross multiply, I get the result that the probability of the intersection is equal to the product of the individual probabilities. So this statement here and this statement here are the same, are equivalent. So let me summarize this. Two events, A and B, are independent if and only if the probability of the intersection is equal to the probability of A times the probability of B. Notice some of you tried to use this fact on example 2 on the exam, question 2 on the exam. Notice it's only true, the probability of the intersection is equal to the product of the probabilities only if the two events are independent. Now, if two events are independent, by the way, then it's easy to show that the complements are independent. I show that right in the text for you, by the way, or I suggest how you can do it in the text. What would I mean by three events? Well, suppose I had events A, B, and C. These are independent if one, P of A and B and C equals to P of A times P of B times P of C. 2, P of A and B, not only all three, but must be all two. All possible combinations. So if you have three events, in order for if they're independent, if all possible products, all possible intersections are equal to the product of their individual intersections. So there are two kinds of problems. How's my time? Okay. There are two kinds of problems that can arise. Problem number one, to use independence to solve a probability problem. Or two, prove events are independent. So there are two, by the way, some people call this stochastically independent. So there are two kinds of questions that one could ask with respect to this concept. Use independence to solve a probability problem. Maybe I'll do a quick example to illustrate that. And example number two is prove two events are independent by examining the probabilities. Where's the example I had here? How's my time? I have, oh, okay. I'm not going to have time to drag out the problem. But I just started the notion of independence. I will work out some problems the next time to show you some interesting results about it. And we'll do independence, and then we'll move on to random variables the next time. Anybody have any quick questions you'd like to ask? This is, I just did 2.4 and I started independence in 2.5. Okay, let me stop this recording.